Okay, good evening to all and welcome to the another session of the NPTEL course Heat Transfer. Today we will be discussing some of the practice questions related to the week 8 topics which are free convection and boiling. Let's have a brief recap of what are the topics that are covered in week 8. It's so till last week we were discussing about the force convection where we discussed about the external force convection, or we can say flow over a flat plate, and internal flows, which is the flow through a pipe or a tank. So now we have the free convection over a stationary surface where when there is no external flow or we are not inducing any type of flow. So because of the temperature difference and a density gradient or a density difference is generated, and this will cause the natural convection of the natural current. That is a free convection. Then concept of boiling were discussed, like cool boiling and flow boiling. And in blue boiling, the Rossinos correlation and the pool boiling curve, were also discussed. So we will discuss some of the questions related to these topics. So let's get started with the first question. Okay, in this we have a zero point 0.6 meter thin square plate in a room of at 30 degrees Celsius. So the ambient temperature is 30. And one side of the plate is maintained at a temperature of 90 degrees Celsius, while other side is insulated, which means uh, the plus plate surface temperature is 90 degrees Celsius. Okay. Assume natural convection is only mode of heat transfer. Determine the convection heat transfer coefficient and the rate of heat transfer from the plate. So the properties of air at film temperature is given, and the Nusselt number for correlation for this configuration or for this situation is also given. So we are asked to find out the heat transfer coefficient and rate of heat transfer from the plate. So this is basically a simple question. So everything is given. So you just need to substitute the values into the Nusselt number, then find out what is the uh, heat transfer coefficient. So this will give the first answer. And from if we get the heat transfer coefficient, we can easily calculate the heat transfer rate. So I will give you 5 minutes to solve this. So please try, because this is so I already told how to solve this. So just substitution of the values, and only here we are here to do is the Rayleigh number correlation. I hope you know what are the expression for Rayleigh number.
Grashof into Prandtl number.
Yeah. So first you have to find out the Grashof number, then just multiply it with the Prandtl number. Okay, I will wait for 5 minutes. I hope you will be able to solve. So I will repeat the question once more. We have a square plate which is at 30 degrees Celsius, and which is kept at a room at 30 degrees Celsius, and the surface of the plate is maintained at 90 degree, and the Nusselt number correlations are given, and the properties are also given. So we have to find out the heat transfer coefficient and the rate of heat transfer from the plate. So please solve this and get me the answer. So anyone got the answer?
I'm just trying, sir.
Okay. Any others got the answer?
Sir, here length is not given.
Length is given. Consider 0.6 meter thick. That is the characteristic length.
At 6 meter thin it is written. So this is thickness or
Yeah,
length?
no. It's like 0.6 meter in length, but the thickness is very thin. Like that, it is. Length is 0.6 meter. What is the value of Rayleigh number you got? So Rayleigh number is Grashof number into Prandtl number. So the Grashof number is G beta Ts minus Pt infinity is delta T L cube divided by mu square. Okay, into Prandtl number. So first we have to find out what is beta. What is beta? It is 1 by
1
Tf.
by T. Yes.
Yeah. So Tf is how much? That is the film temperature is 90 plus 30 by 2. How much?
60.
60. It should be so when while substituting Tf should be in Kelvin or degree Celsius.
I think we should take it in Kelvin.
Yeah, it should be 1 by 333 is the beta value. So if you substitute this, Rayleigh number becomes 9.81 into 1 by 333 90 minus 30.6 the cube divided by mu square. That is mu is given 1.896 and 6 into 10 raised to minus 5 the whole square into Prandtl number is how much? 0.707202. So this is the Rayleigh number value. What is the Rayleigh number?
7.2 into 10 to power 9.
7.10
2 into 10 to power 9.
to the power 9.
Yes.
I am getting 10 to the power 8.
7.2 into 10 to power 9 I am getting, sir. Let me cross check.
Okay. Anybody else calculator?
Yes, sir. 7.2 into 10 to power 8.
Okay. That is. So, but actually, now you got Rayleigh number. Now you can just substitute in this expression. Okay. So you can substitute later because it will need some time to do the mathematics. So after that, you will get the uh, Nusselt number value as around 113.4. Okay. This is known as a Churchill and Shu correlation. So you can refer to some textbooks for its detail. So the Nusselt number will come out to be around uh, 113.4. So you can just calculate and check whether this is coming. Okay. So now as Nusselt number we can find out H, which is equal to Nusselt number times K by L, which is 4 times K is how much? 0.02808 divided by L, that is 0.6. Can you please calculate this value?
5.3.
Yeah, it's 5.3 watt per meter square Kelvin or degree Celsius. Okay. So, now we got H. What is Q? That is first part is we got the first part. What is Q? It is heat transfer rate. That is HAS Ts minus T infinity. Can you please calculate? That is 5.3 area of it's a square. So L square into 90 minus 30.
114.5.
How much?
114.5.
Okay. So the closest answer is 150. Okay. Fine. So this was a direct because so the correlation for generally the correlation of this what to say free convection is very complex. So most of the situations this will be given. Okay. So you just need to substitute these values and find out. So we will try another similar kind of question. So we have a SS ball. It's not a flat plate. So we have an SS ball of certain properties, and we have to remove. It is removed from oven at a uniform temperature of 300 degrees Celsius. So the initial temperature is 300. The ball is then subjected to flow of air at 25 degrees Celsius with a velocity of 35 meter per second. Okay. So the surface temperature of the ball drops to some value. Determine the average heat transfer coefficient during the cooling process. So is this a free convection or a forced convection?
It is forced convection, sir.
Yeah, this is a forced convection case because we are if say for example if the ball was simply kept at ambient air, okay, then it was a case of free convection. But in this question, it is said that the air is subjected to a or is placed in the path of flow of air, which is flowing at 3 meter per second, having a temperature 25 degrees Celsius. Okay, but the correlation is given, so we have to find out the average heat transfer coefficient during this cooling process. So it's it's like a direct, just mathematics only required. We have to do some calculations because the Nusselt number correlation is already given. So you have to find out what is the Reynolds number of the flow. That's all. I hope you can do it. So I'll give some 2-3 minutes to solve it. So can you please try it and what is the Nusselt number value you are getting. Also, first you try the Reynolds number, then we will go to the Nusselt number. First, let me know the what is the Nusselt number? Sorry, Reynolds number of the flow.
Excuse me. Excuse me, sir.
Yes, yes.
This 25 centimeter SS ball, is it dia or radius?
It's a direct. What is the Reynolds number? That is R Reynolds number is V T by mu. Sorry, okay. Kinematic viscosity. Mu. That is V is 30 into what is the diameter? It is 0.25 meter. Yeah, by mu is given. That is 1.562 into 10 raised to minus 5. What is the diameter? Sorry, Reynolds number.
48015.
4.
48015.
Okay, it's like okay, 4.8 into 10 raised to 4. Yeah. So now can you calculate the Nusselt number? So, okay, I will, as it will take some time, I will directly write the value. So I will, you can check later. So it's 0.2 plus zero point 0.4 Reynolds number raised to 0.5 plus 0.0648015 raised to 2 by 3 times Prandtl number is given how much? 0.7296 raised to zero point 0.4 mu infinity by mu s. Okay. Mu mu infinity, that is properties of airstream uh, at surface temperature. Mu infinity is 1.849 into 10 raised to minus 5 divided by mu s, that is average surface temperature, 2.76 into 10 raised to minus 5, the whole raised to 1 by 4 or 0.25. So you'll get the answer as around 135. So Nusselt number. Can you please find out what is H? That is heat transfer coefficient. Nu K by L, which is 135 into K. Point 0.2551 by It's a characteristic length, so diameter is 0.25. What is this answer?
13.8.
Yeah, it's 13.8 watt per meter square. So it's a so this is so we have to estimate. It's a continuation of the previous question. So based on the question number two, we have to estimate how long this process of cooling will take place. It's like a transient heat transfer problem. Okay. So I will tell how to proceed. So then you can. So otherwise, can you tell how to solve this? You have to estimate how long this process of cooling will take place. How long it will take from how long it will take for the board to cool from 300 to 200 degrees Celsius, right? Yeah, temperature drops to 200 degrees Celsius. That is the question.
Sir, first we will find the total amount of heat, that is QMC delta T, and then we will divide it by rate of heat transfer.
Yeah. So can you please find out? First, we have to ask you, sir. First, we have to find out what is the uh, amount of heat that is rejected. So the amount of heat that is energy that is rejected by the board from this MCP dt equation. Then we have to find out what is the convective heat transfer rate. So so when we divide by rate, it will get the total time that is required for cooling. What is Q board? That is MCP dt delta T. So M is how much mass of the board we have to find out. That is rho times V. Density is given and we have to find out the volume. That is M is equal to rho times V. That is equal to rho times pi by 6d cube. Okay. So that is density is 8055 into pi by 6 into 0.25 whole cube. You will get us around 65.9 kg. And Cp is already given, which is uh, 4 480 joule per kilogram. We just substitute this value, that is 65.9 into 480 into 300 minus 200. Can you please find out what is Q board?
Three point two into 10 to power 6.
How much?
3.2 into 10 to power 6.
Okay. What is the unit?
Yes.
Unit.
Unit will be joule.
Yeah, it's in joule. Now we have to find out what is the rate of heat transfer. Okay, by convection is Q dot average. As it is a rate that I am taking. So HAS, that is heat transfer coefficient, into the surface area divided by TS average, the average surface temperature, minus T infinity. So the TS average is like the T initial plus T final by 2. This is a rough way of calculating uh, this q dot average. Otherwise, it's a simple process. Otherwise, you have to go with the like the lumped. Sorry, we cannot use it. I think we may not be able to use the lumped capacitance model. So you have to go with the normal semi-infinite solid or the correlations for or the graphs that we already discussed in the previous session. The graphs for this kind of spherical poles having transient heat transfer. But here we can have a simple estimation of what is the q dot average. But if you want more accurate, you can as an exercise you can do that kind of analysis also, and you can find out the difference. How much is the difference between this q average and the actual transient heat conduction? So it's like 300 plus 200 by 2, so it will become 250. Okay. So what is the h? Can you please estimate this the h? Sorry, h we find out that is 13.8. The surface area, what is the surface area?
4 pi r square.
Surface area, it's a sphere of the sphere.
4 pi r square.
4 pi r square. Yeah. Yes. So if we convert that to you can as we have I have taken diameter, it's equivalent to uh, what to say pi d square into ts average. Sorry, ts average is 250 minus t infinity is how much? 25. So if we calculate this, we'll get 13.8 into 5 into 0.25 the whole square. 250 minus 25. What is this answer?
609.3.
60
609.4.
60
609.4. 0.4.
604.
0.4, sir. 609.4.
609.4 watts. Okay,
Yes, sir.
it's like joule per second. So the time required is, can you please find out what is the time required for cooling? Is Q4 divided by Q dot average is equal to 3.2 into 10 raised to 6 joules divided by 609.4 joule per second.
Sir, it is coming out to be unreasonable actually. It is very high.
Yeah, let's get what is the value?
5 to 5.1.
5 to
5.1.
second, right?
Yes.
Yeah, it's when we divide by 3600, it is close to 1.5 hours. It's fine. Okay, it's close to 1.5 hours.
Yes, yes.
Why it is? Because the H is very low. Say for example, if you are dipping it or if you are placing it in a stream of water, okay, so the H will be very high and this will reduce to some seconds. As it is air, and also how we can increase this Q average. Either we can send the air of lesser temperature. So instead of 25, if we reduce the air temperature to some 10 degrees, okay, what is the Q? What will be the Q? Can you have a just rough calculation?
Can you please repeat?
Instead of 25, if the air we are sending is at 10 degrees Celsius, So the Q means don't need not be calculated. So I just calculated it will be around 650 joules per second. So so accordingly the what to say the time required for cooling will reduce. So that is one way. What is another way of increasing heat transfer? You can increase the Reynolds number, right? From 3 meter per second, you can increase to 10 meter per second. Like that, you can change the heat transfer. I was just mentioning what are the different ways, what are the parameters that are affecting the heat transfer. Okay. So, okay, this is another question. So this is a similar kind of question we have uh, done in the last class, last week. So I hope you will be able to solve it. So I will give some 5 minutes for you to solve. So we have a steam in the condenser of a power plant is to be condensed at a temperature of 30 degrees Celsius. So that is very important. The steam is condensing at 30 degrees Celsius. Okay, which enters the tube of the condenser at 14 degrees Celsius and the water. Okay, the cooling water enters at 14 degrees Celsius and leaves at 22 degrees Celsius. The surface area of the tube is given and the overall heat transfer area is also given. So the condenser is well insulated so that the heat loss towards the surrounding is negligible. So which means the heat transfer uh, is only within the steam and the flowing fluid. Okay, so we have to determine the heat transfer. So can you please say the steam is condensing at 30 degrees Celsius? Right? So the question is is it right or wrong? Or if it is right, when this can happen? The first 5 marks, please. Is this statement correct or is it right or wrong? Can steam condense at 30 degrees Celsius?
It is a surface temperature actually. So constant surface temperature condition is made.
No, no. It's the steam condensing. Okay. So whether the steam can condense at 30 degrees Celsius. Okay, because of the condensation of the steam, the tube wall is maintained at 30 degrees Celsius. It can happen if we are decreasing the pressure. Okay. If you reduce the saturation properties, so if you reduce, I mean, steam condensate at 100 degrees Celsius, only at what pressure?
1 atmosphere.
Yeah. So if we change the pressure, the saturation properties will change. Okay. So just so this kind of questions can also come. So that's why I just give you a hint. Okay. So can you please do this? For that you need not worry about this kind of saturation properties and all for solving this question. So I will wait for 2 minutes. Please let me know the answer. Have you got the answer?
Yes, sir. It's 1087 kilowatt.
Yeah, it's almost close to 10. How much?
1087, sir. The C
Okay.
option. C option
o-
is there.
Okay, okay, fine.
Actual my answer is 1086.8.
Okay,
So option is 1087.
yeah. So, what is A? So let me check. A is 45 meters square. Okay. So, so the overall heat transfer coefficient is Q100 watt per meter square Kelvin. Then, what is the, so what is Q? First, that is UA delta T. Is this LMTD or just normal delta T?
LMDD, sir.
Yeah. So first we have to write out LMTD delta Ti minus delta TO divided by Ln delta Ti by delta TO. So this is delta Ti. How much it is? The T minus delta Ti. It is 16 degrees Celsius, and this is delta T is 8 degrees Celsius. So 16 minus 8 divided by Ln 16 by 8 is 8 by Ln 2. Am I right? What is
Yes,
this
sir.
answer?
11.5.
11.54. Now it's like simple. U is 2100 45 and 1.45. So you'll get what is the answer? 1087 kilowatts. So that was a simple question. We already discussed this kind of question in the last class. Now it's a continuation. So we have to determine the mass flow rate of the cooling water and the condensation rate of the steam. Do you have any idea how to find out this? Let's first find out what is the uh, condensation rate of steam. So how to find out that? Okay, then what is how will find out the cooling mass flow rate?
Sir, that can be MC delta T. Q dot is equal to MC delta T.
Yeah, okay, that's right. How to find out the steam condensation rate? So the water,
That mass flow rate is to be divided by latent heat.
yeah. So for that you so first find out the water, cooling water. So Q is equal to m dot W Cp delta T. So m dot W is equal to Q is how much? 1087 divided by Cp. You can take 4180 into what is delta T is 22 minus 14, which is 8. So can you find out what is this answer?
32.5.
Yeah. Look, fantastic. Next is the mass flow rate of steam or the condensation rate of steam. That is a perfect one. As there is no heat losses, this Q is equal to m dot S HFG. Okay. So m dot S is equal to Q divided by HFG. So our task is to find out what is HFG. So you have to go to the saturation steam table and find out the what is the saturation properties of steam at 30 degrees Celsius, with steam condensing at 30 degrees Celsius. So I hope you know how to take out the use the steam tables and find out the value. So if you find out that, you will get Hg as kilojoule per kilogram and Hf as, so how to find out HFG? Just simply Hg minus Hf, you will get 2429.86 kilojoule per kilogram. Finally, please find out what is m dot s. Is 1087 into 10 raised to 3 divided by 2429.816 into 10 raised to 3. What is this answer?
Point 5.
0.5. Okay. You can just, I'm getting some 0.45. Okay, you can just cross check. And this is the concept. Okay. So, yeah.
I am also getting, sir, 0.447 actually.
Okay. So let's move on to the next question. So this is a boiling question. So we have a copper pan having a diameter of 150 mm. The bottom of the pan is maintained at 115 degrees Celsius when placed on an electric cooking range. Estimate the heat required to boil the pan in this water. Also determine the critical heat flux also. So the properties are given. So this is a question from the boiling part. Okay. So what is the correlation we usually use for, assume this is a nucleate boiling. So what is the correlation we use for nucleate boiling regime? Or under for flow boiling, sorry, pool boiling. Are you aware of that? This correlation, which is a famous correlation, is usually used.
I think Rosen. Oh, I
Yeah,
think
it's
Rosen.
not as Rosenow correlation. So you have to use that correlation for finding out. Okay. So the correlation is not given here, so I will write the Rosenow's correlation for you to calculate. So the Rosenow's correlation, the heat flux, surface heat flux is mu L, which is the viscosity of the liquid, HFG, latent heat of vaporization, T, rho L, that is the density of liquid minus density of vapor, divided by sigma, the surface tension of the liquid, half into Cp, that is specific heat of liquid, delta T, that is the surface superheat, CSF. CSF is a coefficient which depends on the solid fluid combination which we are using. HFG again, Prandtl number raised to an exponent n raised to 3. Okay. So this is the Rosenow's correlation. So for finding out the Rosenow's correlation, or finding out what is the heat flux. Everything is given. That is the this is a solid. This is a coefficient which determines or which depends on the solid fluid combination. So actually, if you can see any standard heat transfer textbooks by Incorpor and all, you can see a table which gives the value of the CSF for various surface fluid combinations. So for water, copper, for polished surfaces, it's normally for it's 0.012, which I think which is given. Okay, it's 0.012, 0.013, which is for a water copper combination for a polished surface. So for example, if you are using a stainless steel pan, okay, so this CSF value and the N value will also change. So for example, for a mechanically polished surface of stainless steel with the water combination, this CSF value is 0.0132. So it will be given usually. Okay. So and the exponent is 1. So like that, this will change depending on the solid surface fluid combination. So this particular question, we have a copper pan and a water. So that's why the CSF and 1 is given, and the properties of water is also given. So you will get what is the heat flux. Then if you get the heat flux, we can find out what is Q, right? How to find out? If we get the flux, it's just multiply with the surface area of heat transfer. So can you please find out what is this Q dot S? So this is some calculation intensive, but I will wait for some 2 minutes. So please try, because this kind of questions can come in maybe descriptive kind of examinations. The calculation speed is also very important. Okay, I will. So it's like Q dot equal to mu L 279 into 10 raised to minus 6 into HFG 2257 is 9.81. New L is 957.9 minus 0.5 sigma 3 raised to half CPL is 427 into delta T is how much?
Yes, sir. This delta T, I'm not able to calculate because 115, the bottom pan temperature is given, but that boiling point is not given.
Boiling point, if it is not given, you can take 100 unless it is specified.
So here it is not given.
Eh?
Here it is not given.
100. It's water.
Water, okay, then water at 1 atmosphere it will be
Yeah,
100.
100 degrees.
Yeah.
If it is not given, you can take this. Otherwise, you have to check whether the boiling point is given or not. 3 CSF is 0.013 into HFG 2257 into 10 raised to 3. This should be also 10 raised to 3 into 1 point. Sorry, what is primary number? Raised to 1. If you calculate this, you can check later. So it will you will get close to 4.619 into 10 raised to 5 watt per meter square. Okay. So just Q,
Sir,
that is a yeah.
here, can we take this rho L minus rho V equal to rho L? Like density of liquid minus density of vapor, we can take density of.
Yeah, there it won't be much difference, but yeah, can take.
Okay.
It's better to calculate if it is given. Okay. So Q is equal to the heat flux times the surface area is 4.619 into 10 raised to 5 into the surface area of the pan, what is diameter of the pan, 150 mm, which is 0.15 meter square. Sorry, 0.15 meter. We'll get 8.16 kilowatts as the heat that is required to boil the water. It's a heat that is applied to boil the water. Okay. Now we have the critical heat flux. That is also the correlation is given. Okay. So that value is Q critical. The maximum heat flux that can be given is CHFG rho V divided by rho V square raised to 1 by 4. Okay. So I'm giving the final answer because everything is given. So this C value you can take. So this C is different. So this critical heat flux is independent of the surface material and is weakly dependent upon the heated surface geometry. Okay. So so this C is we have different values of C. So it is experimentally found out. So for large horizontal flex, so we can assume this as this copper pan as a horizontal plate. The C value is usually given or taken as 0.149, and for long infinite for horizontal spheres and cylinders, so this is usually taken as 0.131. So usually it will be given. So this is an experimentally found value. Okay, this C value. So if you substitute this, you will get the critical heat flux value as around 1.26 megawatt per meter square. Okay. So this I'm giving you as a homework. You can just try in the next class and come. Okay. There's nothing wrong. The only thing you can get wrong is the calculation. Okay. So because everything is given, it's a direct calculation. Okay, let's move on to the first next problem.
Actually, sir, in this previous program, what is the critical heat flux? Means the maximum heat which can be transferred, or
No, actually, I hope you are you have seen the boiling curve. Okay, so in the critical heat flux is the maximum heat flux point. Okay, where which can give uh, which is like the dry. Are you aware of dry out? So if we it at this critical heat flux point, critical heat flux, the there will not be the water will not or the surface or the whatever liquid, the liquid will not be in a, come in a, will not be able to come in contact with the surface. So this will increase the temperature of the surface, and this can go beyond the melting point of the surface. So this is known as the, like it is known as a burnout point, which is very essential. It is commonly known as the burnout point. Or okay, so beyond this point we cannot go. So if we go beyond that point, it can damage the surface or it can lead to the melting of the surface. So like so it's very important to before designing a two-phase device like which involves the boiling. It's very important to find out what is the critical heat flux. We should not give a heat input above this critical heat flux. Okay, I hope it is clear. So let's move to the next question. So we have a silicon chip which has a thickness of 25 mm and has a thermal conductivity of 135 watt per meter Kelvin. The chip is cooled by boiling a saturated fluorocarbon whose saturation properties is given on its surface. The electronic circuit on the bottom of the chip is perfectly insulated. So the nucleate boiling constant circuit. What is the steady state temperature at the bottom of the chip? The properties of the fluorocarbon is also given. Okay. So you have to find out what is the steady state temperature at the bottom of the chip. I hope you understand the question. So we have a silicon chip of particular thickness, and on the top of the chip, it is cooled by a by boiling or by full boiling of a saturated fluorocarbon. It's like an emulsion heat. So its saturation properties are given. So we have to find out what is the steady state temperature at the bottom of the chip. So how to proceed this question? First, what we have to find out.
first we have to find out the heat flux?
Yeah. So for finding out the heat flux, what can we use? The Rosno's correlation that I already discussed in the last class. Sorry, last question. So you find out the critical heat flux. Sorry, not critical heat flux, the heat flux according to this.
But sir, that equation we are talking, that Rosenhow equation, that is for boilers, that is for water. But here the fluid is different.
No, Rosno, it's not for water. So it is not only for water. That's why I told about this That's why they incorporated this. What is this? I already told in the last class. Sorry, last question. What is this CSF?
That is the surface fluid property, that is surface and the fluid properties related to.
Yeah, it represents the uh how to say fluid surface combination. So it is different. It can be if it is given, it is 0.005 for this fluid surface combination. It not only depends upon water, it depends upon any fluid. So that's why this CSF and N values are given. So you can assume that the surface temperature of the chip is 15.9 degrees Celsius. Now you can find out the Q, which is the surface temperature, where it is in contact with the fluid. Now you can find out what is the heat flux, which is the which is it's like, so this is the plate. Sorry, this is the chip. So this is the Q. Is the Q heat flux that we will get from the Rosenow correlation. So this will be the heat flux that will be conducted. So if we find out the heat flux or the heat flux from the Rosenow correlation, equate this with the conduction Fourier's conduction equation, you will get what is the bottom surface temperature. So this Q boiling is equal to Q conduction will be equal to Ks, that is the thermal conductivity of the chip, Tb minus T surface. This is Tb, T surface. Tb is what we need to find out by L. Okay. Or L is the thickness. L is given as 25 mm. So that is the Rosenow correlation. That is Qb is equal to uh, mu L HFG G rho L minus rho V by sigma half CPL delta T. So this is not, so if the T surface is 15 degrees Celsius, it won't, boiling won't take place, right? So the T surface is one. Let me check the question. So the T surface you can take it as around 20 to 73 degrees surface temperature of the chip. Now you can calculate everything. What is delta T? T surface minus the T infinity or the T is the boiling point of the liquid divided by CSF HFG Prandtl number raised to N. So the properties are given. Mu L is 440 into 10 raised to minus 6. HFG is 84.4 into 10 raised to 3 and 0.81. 619.2 minus 13.4 by sigma 8.1 into 10 raised to minus 3 is to half. So here it is 3 is the into CPL 110 into is 1110 okay, into 73 minus 57 CSF 0.005 HFG 84.4 Prandtl number 9.01 whole raised to addition 1.7. If you do that, you will get the boiling heat flux as around. You can do the calculation later. So it will be around 5 into 10 raised to 4 watt per meter square. This will be the Q for the boiling heat flux. So this you can equate to.
I think, sir, you should put that on the last term, the cube also, no?
Yeah, it's a cube also.
Okay, yeah.
So this you can calculate with TS or the T silicon, sorry, K silicon minus T base. That is where we have to find out T by L. So what is TB? Is 5 into 10 raised to 4. The thickness of the chip is 25 mm, that is 0.025 divided by what is the case thermal conductivity is given as 135. Okay, 135 so this is not 25 mm, sorry, okay, this is 2.5 mm. 2.5 mm because cannot expect a chip of 2.5 centimeter thick. Okay, this was a typing mistake. 0.0025 plus 73. Can you please find out what is TB? What is TB?
73.9.
Yeah. So, this question is a continuation. If the chip bottom heat flux is raised to 90% of the critical heat flux value, so what is the new steady state value of the chip temperature? So, can you please find out what is the critical heat flux value? So, I think for that you need the C value. So, the C value we have taken 0.149. So, the critical heat flux or the maximum heat flux is, I'm replacing it with 0.149 HFG rho V, rho L minus rho V square raised to 1 by. Yeah. So this is 0.149 into HFG. How much is the HFG? Yeah, 84.4 10 raised to 3. Rho V is 13.4. Sigma 8.1 into 10 raised to minus 3 into 9.8 into 9.2 minus 13.4. 13.4 the whole square. So if you do that, you will get the critical heat flux as this much. Okay. So, but this is not the heat flux we are asked to find out. So we are asked to find out the chip bottom temperature when the chip heat flux is raised to 90% of the critical heat flux. So just multiply it with 90 percentage or 0.9, and can you please calculate the what is the surface heat flux? Sorry, surface temperature. What is the heat flux? That is, we need to calculate, which is 0.9 times is equal to around 13.9 into 10 raised to 4 watt per meter square. Okay, but we have to know what is the surface temperature. Okay, so no need to calculate the whole value. So if you see this equation, okay, so the only thing we can change when the heat flux changes is what? The variable which changes when the heat flux, we increase the heat flux. What is the variable in this equation which can change with heat flux? Can you identify?
Delta T.
Yeah. So we can write Q boiling, or we can generally write Q heat flux as K times delta T raised to 3. So K is a constant which comprises of all of the other terms. Okay. So the delta T, so this is delta T1, which is the first case, we can say. So delta T, or the heat flux of the second case, is delta T 2Q. So this is what we need to find out. Okay. So just divide it. You will get delta T2 is equal to delta T1 into how will it will become? Yeah, Q2 dash divided by Q1. If you divide this, yeah, it will be right. Q2 double dash by Q1 double dash raised to 1 by 3. Okay. So can you please find out what is the answer? Which is delta T is you will get some, what is the value? 16. You already find out 16 times. So this value will come out to be around 1.41. You can just try later. Okay. So which will become 22.4 degrees Celsius. Which is the new surface superheat. So now from the conduction equation, that is Tb2 is equal to T surface 2 plus, what is T surface 2 is equal to delta T2 plus T Ts, or sorry, T saturation is equal to, will become around 79.4 degrees Celsius. So 13.9 into 10 raised to 4. So it is equal to 79.4 plus 13.9 into 10 raised to 4. So you'll get the answer as 82 degrees Celsius. So this will be the surface temperature when the heat flux is increased to 90% of the critical heat flux value. Okay. Let's move on to the next question. So
Sir, in this question, you have earlier assumed TS to be 78 degrees Celsius. That
yeah,
I'm not able to understand. Here and in the top, if you move up,
yeah, I already told
yeah,
TS is 73 degrees Celsius.
okay. So this is the data which will be given in the problem.
Question. Yeah,
Yeah, okay.
I
Okay,
missed to write the question
okay
part.
then. Okay.
So we'll go to the next question. We have a saturated steam which is condensing, which is at zero point 0.1 atmosphere, condensing with a convection coefficient of 6,800 watt per meter square Kelvin on outside of a brass tube having inner and outer dimensions given. Okay, respectively. The heat transfer coefficient of water flowing inside the tube is also given. Assuming that the mean water temperature is 30 degrees Celsius, calculate the steam condensation rate per unit length of the tube. So how to do this? We have a step two. So its inner and outer dimensions are given. So the water is flowing inside and the steam is condensing here outside. Okay. So what we have to first do? We have to first find out what is the surface temperature of the outer surface temperature of the brass tube. Am I right?
Yes, sir.
Yeah. For that, you have to find out from the steam table what is the saturation temperature at 0.1 bar. Okay. So if you refer to the steam table, you will get the saturation temperature at zero point 0.1 atmosphere. It may be in bar, so you have to do the calculation accordingly. So which will be approximately 320 Kelvin. This is the saturation temperature. Okay. So the outer surface temperature will be 320 degree. It's not 320 degrees Celsius, 320 Kelvin. Okay. So now we got this, and the outer heat transfer coefficient is given, that is 6800 watt per meter Kelvin, and inside heat transfer coefficient is also given, meter square Kelvin. So the outer diameter is given 19 mm, inner diameter is given 16.5 mm, and the thermal conductivity, the thermal conductivity of the brass tube will be also given. So you can take the K of brass. So because uh, it is, you can take 110 watt per meter Kelvin. Okay. Thermal conductivity also fast. So what is the resistance? It is overall resistance. I'm writing based on the outer diameter. You can write based on inner diameter also. So 1 by UO is equal to 1 by HO plus RO by K. Okay. Ln D, it can be DO or RO because it's division, right? So DI plus, this can be also DO or RO because it's division, 1 by HI. So this is the resistance network. So you have to find out 1 by 6800 plus this RO, it becomes mm, right? So it will be divided by 2, it will be 9.5 mm. So 0.0095 by 110 ln 19 by 16.5. So because I'm writing it because it's a division, so there is no need of converting to the actual meter, or because it will cancel out. So the symbol that is 19 divided by 16.5 into 1 by HI, that is 5200. So if you calculate this, you will get the outer heat transfer coefficient based on outer area. You ask 2627 watt per meter square K. Okay, now how to find out? Can you please find out? Can you please say how to find out the, what is the question? The condensation rate per unit length. How to find out it?
First, find out the flux, heat flux.
Okay,
No, no rate of heat transfer. Sorry.
here, okay, heat transfer rate, that is Q, it is equal to, as it is told, it is per unit length, so I'm taking as L as 1. Okay, so U0, and I'm writing it based on the outer surface area. So pi D0 is saturation minus the mean temperature. Okay, so the mean temperature of the water is given. So which is equal to m dot of steam into HFC, right? So this is equal to, you can simply calculate pi into 19.5, right, or 19. HFG, you have to find out at this, what is the HFG by checking the steam tables. So it will be, I hope you know how to use steam tables. So this will come out to be around 1.11 into 10 raised to 3 kilogram per second. So the only task here was to find out what is the saturation temperature of steam at zero point 0.1 atmosphere, and also the uh, latent heat at this saturation properties. Next is a simple conduction equation. We already discussed several type of similar kind of questions during the initial lectures or initial sessions. Now we will go to the next question. which we have a bottom of a copper pan, which is a diameter 0.3 meter diameter, is maintained at 118 degrees Celsius by electric heater. Determine the critical heat flux of this situation. So the saturation properties are also given. So as is a similar kind of question, I am just writing the answer. Okay. So the saturation properties at 100 degrees Celsius. So the water is boiling at 100 degrees Celsius. Okay. What is delta TE? Can you just look and say what is delta TE?
18.
Yeah. It is 118 minus 100 is 18 degrees Celsius. Okay. Then everything it's given, that is what so the what is the critical heat flux value? That is 0.149 HFG rho V sigma G rho L minus rho V by rho V square raised to 1 by 4. Okay. So it's equal to 0.149 into HFG is given how much? 2257 into 10 raised to 3. Rho V is given, that is 0.1596 into sigma 58.9 into 10 raised to minus 3 and 0.81 into rho OL 957.9 minus 0.5956 the whole raised to 0.5956 the whole square raised to 1 by 4. Okay. Raised to 1 by 4. So this is continuation of this. Okay, it's not a separate one. So you will get the maximum heat flux as around 1.26 megawatt per. So this is the maximum heat flux. So beyond this heat flux, you shouldn't apply the heat because of the safety aspect. Okay, this is the region where the film boiling happens, and where the surface, the water will not be come in contact with the heated surface, and the temperature will increase drastically, and it can lead to the damage of the appliances or the melting of the substances. Okay. So as an engineer, always we should find out what is the critical heat flux when we are dealing with, because we should have a upper cap or a limit to the heat flux that can be provided. We shouldn't go beyond this critical heat flux value. Okay. So here it comes to the end of our session. So I hope the session was helpful for you, and you are you try to. Yes.
Okay, sir. Thank you. Yeah, it was very helpful.
Yeah, and I think you are able to follow it up. And have you registered for the exam, or are you just auditing the?
Yeah, I have registered, sir.
I hope this kind of my session will be helpful for your exam point of view also.
Okay, sir.
So
Yeah,
yeah,
thank
thank you, and all. Have a nice week ahead. See you next week. Thank you.
you. Thank you, sir. Thank you.